Okay, in this particular section, or rather episode, we will discuss two another applications of Gauss theorem. First, we will discuss electric field at a point due to uniformly charged spherical shell. Spherical shell is a hollow sphere over the surface of which the charge is uniformly distributed. So, charge is uniformly distributed over the surface of a hollow sphere. So, distribution of charges on an area. So, it's a two-dimensional case. And as we are aware, in one dimensional we make use of the term linear charge density, which is represented by lambda, charge per unit length. In two-dimensional, we make use of the term surface charge density, which is charge per unit area. And in three-dimensional, when the charge is uniformly distributed throughout the volume of the body, then we make use of the term rho, which is known as volume charge density, defined as charge per unit volume. So anyway, so this is a two-dimensional case, charge uniformly distributed over a spherical shell. So it's a 2D case, making use of sigma. So we will try to find expression for the electric field in terms of sigma due to this uniformly charged spherical shell using Gauss theorem. So this is another very important application of Gauss theorem, right? So for this, what we consider is, we will consider a shell. Shell means a hollow sphere. This is a shell. Say this is the center and radius r. Say radius is smaller. Or rather, let's consider the radius of the shell to be represented by capital R, because we consider the distance of the observation point as smaller from the center. So here charge plus q is uniformly distributed over its surface. This is the charge q, which is uniformly distributed over its surface. So it is a shell, uniformly charged spherical shell. So obviously we will make use of the term sigma. It's a 2D thing. So it is defined as charge per unit area. Net charge is q. Area, this charge q is distributed over the surface area of this spherical shell, which is 4 pi r square. So charge can be written as 4 pi capital R square into sigma, right? So this is the net charge. Okay, we need to find out, suppose electric field at point P, which is lying outside the spherical shell. So let us assume the distance of this observation point from the center of the spherical shell be smaller. So case 1 is when smaller is greater than capital R. It means that we are dealing with the case whereby the observation point lies outside the uniformly charged spherical shell, right? And as I mentioned, in order to determine the electric field over here, we are using Gauss theorem, and in order to use Gauss theorem, we need to consider some Gaussian surface. So in this scenario, a spherical Gaussian surface is preferable. So let us consider a spherical Gaussian surface passing through point P and coinciding with center O. Its center is at point O and radius smaller. So Gaussian surface, it's an imaginary surface which we have assumed, so it has to be represented by dotted line like this. There is a spherical Gaussian surface of radius smaller passing through point P. Now, as per Gauss theorem, we know that students do one thing. Whenever Gauss theorem is applied, now whenever you write the mathematical statement of Gauss theorem, just recall the theoretical statement. Simply recall the theoretical statement. Electric flux, which is numerically equal to the closed surface integral of the electric field, which is numerically given by 1 by epsilon times net charge enclosed. This Gaussian surface encloses the entire charge q. So this is the statement. Now let's try to evaluate it. This is ds. This is the area vector of Gaussian surface. Small elementary portion of Gaussian surface. So this is the Gaussian surface. So let us consider a small elementary portion like this. This is a small elementary portion. Area vector, it's always perpendicular to the surface and in the outward direction. So this is the area vector perpendicular to the surface and in the outward direction. Electric field. Now, due to this charge, we can always consider this charge to be constant at the center. So, due to this charge, the electric field is also in the outward direction. So, this one will be the direction of electric field. So, here both are in the radially outward direction. So, let's try to evaluate it. E, ds, since both are constant, it's pretty evident from this particular diagram. Both are in the radially outward direction. So, angle between them is 0 degree. It is q by epsilon. Electric field at any point on the Gaussian surface being equidistant from the center would be constant. So, it can be taken outside. Integration of ds, cos 0 is 1. It is equal to q by epsilon. Integration of ds, that will give us the total surface area of this Gaussian surface. The radius of this Gaussian surface is smaller. So, total surface area of this Gaussian surface would be 4 pi small r square. So, therefore, electric field at point P, which is lying outside the uniformly charged spherical shell, would be given by Q over 4 pi epsilon r square. Now, look, this is a formula which we are familiar with. This is the formula for a point charge as well. So, that's an important conclusion. Whenever the observation point lies outside a uniformly charged spherical shell, then the entire charge on the shell may be assumed to be concentrated at its center. That is what we have proved over here, right? Now, in order to obtain the expression for electric field at point P in terms of sigma, substitute this value of Q over here. So, what we get is 4 pi capital R square into sigma, or simply substitute the value of Q from here. So, 4 pi epsilon R square. Therefore, electric field is 4 pi get cancelled, sigma R square divided by epsilon small r square. This is the expression for the electric field at point P, which is lying outside the uniformly charged spherical shell. And this is when smaller is greater than capital R. So, capital R is the radius of the uniformly charged spherical shell. P is the distance of the observation point. So, electric field obey inverse square in such a case. Do remember this particular point. So, this is case 1, right? This is case 1. Now, let's consider case 2. Case 2 is, suppose the observation point lies at a point on the surface. It lies over here. It lies on the surface of the uniformly charged spherical shell. So, it is but obvious from the diagram, it's pretty clear. In this case, smaller would be equal to capital R. In case observation point P lies on the surface of the uniformly charged spherical shell, then smaller would be equal to capital R. So, no need to derive it again, simply substitute this value smaller as capital R over here. So, what we get is, it would be equal to sigma by epsilon. These two becomes equal. So, we are left with sigma by epsilon, which is constant and maximum. So, this is the formula for the electric field at any point on the surface of a uniformly charged spherical shell. So, this is maximum. Let's consider case 3. When the observation point lies inside the uniformly charged spherical shell. So, we are dealing with this case when smaller is less than capital R. You can observe we are dealing with all the cases. Smaller greater than capital R, that's case 1. Smaller equals to capital R, and third is when smaller is less than capital R. Suggesting that the observation point lies inside the uniformly charged spherical shell. Here, again, in order to find electric field at point P, we will consider a Gaussian surface, which is spherical in this case. So, this is a spherical Gaussian surface. Now, if we apply Gaussian theorem over here, what we get is phi is equal to closed surface integral of electric field 1 by epsilon times net charge enclosed. All the charges residing outside this Gaussian surface. So, this Gaussian surface doesn't enclose any net charge. So, net charge over here is 0. So what do we conclude? E dot ds is equal to 0, which means that electric field is 0. So electric field at any point inside a uniformly charged spherical shell is 0. So you need to remember these 3 points, right? Electric field at a point outside the uniformly charged spherical shell, it obeys inverse square law. Electric field at a point on the surface of the uniformly charged spherical shell, it is constant and maximum value. And at a point inside the uniformly charged spherical shell, the electric field is 0. So, keeping all these points in mind, we can plot a graph showing the variation of electric field with distance r. Now look, we'll draw that graph. So, suppose electric field is represented along the vertical axis and distance is represented along the horizontal axis. Suppose the origin represents the center of the spherical shell, like this was the shell. This was the uniformly charged spherical shell. We know that inside the uniformly charged spherical shell, the electric field is 0. So, at this point, electric field is 0. Right? At r equals to capital R, on the surface, here electric field is 0. On the surface, it is maximum. So, suppose this represents maximum value. Suppose this represents maximum value. And thereafter, at a point outside the uniformly charged spherical shell, it obeys inverse square law, so the graph would be somewhat like this. At a point outside, electric field varies in this particular manner. So this represents the variation of electric field with distance r in the case of a uniformly charged spherical shell. So this graph illustrates